All right, now let's use the techniques that we previously learned in order to solve systems of equations, and specifically a 2 by 2. And we're going to be using the matrix equation given here. Okay, and now let's break it apart and see what it is. So here I've given a system, 2 equations and 2 unknowns. What we have to do is identify what we call the coefficient matrix. And all that is just all of the values that are coefficients to the variables. So in the first one, it's a 2, then it's a 3, then it's a -1, then it's a 2. So we're just taking these values right there. Okay. Well, what does this b? Well, the b is really the constant. Okay. So all we have to do is take 6 and 3, which come from this area right here, the constants. All right. So now that we have identified a and b, we can now use this information in order to calculate the inverse matrix of A. So what I've done here is this specifically works only for 2 by 2s, and I've made it clear over here as well, and I'm going to reiterate it. Okay, I mean the inverse will only work for a 2 by 2, but the process will work as long as the matrix is invertible. So if we're given some matrix that has A, B, C, and D, we can find the inverse by taking 1 over the determinant, which is the AD minus BC, and we just multiply that scalar by the inverse matrix. And what we're doing here is, if you want to see the pattern just quickly, we're flipping A and D, and all we're doing to B and C are changing signs. Okay, so if B was positive, it will become negative in the inverse. If B is negative in the original matrix, then it will become positive. Okay, so let's take all these values now. So in our matrix here, it's clear to see that, well, let me see if I can use different colors. I think that helps. So let's use, yeah, we'll use red to start. So this 2 is A, and let's use pink. This element 3 is B, and green. This -1 is element C, and that leaves blue. No, we can't use blue. How about brown? And this 2 is element D. So now all we have to do is input the values where they belong. So since I used brown last and I have it selected, I'm just going to put the 2 where the D is located, as given by the formula for the inverse. And then I'm just going to substitute all of the other values here. And I believe A was red, so that was a 2. And now I need B and C. Well, B is 3, but it was hot pink, so that's 3 there. And C was green, and that was a -1. So now all we have to do is exchange a few of these elements within the inverse matrix. So D was brown, so that would be a 2 up here. Notice that that's all I'm doing is following the formula. And then all I have to do now is put in, well, B, what color did I use as B again? Hot pink. Okay, so B would be, well, you know what, let's do it this way. Better. We'll just switch the A and the D first, so that makes the most sense. So those two switch. Even though they're the same number, trying to use the colors to show you that they are switching. And now all we have to do with B and C is change the signs. So B was 3, and it was hot pink, so now it becomes a -3. And C was a -1, and it's green, so now it becomes a +1. So all we have to do is the computations here, and the determinant tells us that we do in fact have a solution. What we do, if it's positive, we'll have a solution. So the only thing that you have to worry about is that the determinant cannot be equal to 0. That's no solution, okay? But that's not the case here. So what do we have? 4 plus 3, or 7. So we have 1/7 of this invertible matrix. Okay, now that we have this, the crux of everything, now we can solve the system without any problem whatsoever. And like I said, this will work for a 3x3, 4, but it'll work for any invertible matrix. The only problem is the inverse won't work because it obviously is only for a 2x2. So how do we calculate the solution? Well, the solution given by this notation, so this will be the solution to the system, and that obviously is going to have two components, the x and y variables. Generally, it could be something else later on, is equal to the product of the inverse matrix of A times the vector, or the constant B. Let's just call it that. So now all we have to do is put these all together. So let's put them together. So the inverse was 1/7 2, 1, -3, 2 times the constant, which I believe was 6, 3. So remember, we're just placing these guys that we did all the work for. And my advice here, the advice would be multiply scalar last. Okay? So if we do this product now, then we can do it by the linear combination method very easily. Now, let's just decide what is the product going to have. Well, we kind of already know, because we know what we're solving for is a 2x1. So that means we only have one column to worry about, which is really nice. So that means that we have 1/7, and watch what I'll do here is I'll use the colors. So 6 multiples of the first, so 6, 2, 1. And let me just use black for the plus, for the combination. And we'll use purple for 3. And we'll take 3 of the secondary. And now we can perform the general scalar multiplication. So let me just rewrite 1/7. And now it's going to be 6 times 2, which is 12, and 6 times 1, which is 6. And then we're going to add that to this little beastie, which is going to be -9, and this beastie, which will be 6. And now we just do the combination. So 1/7. Now we'll put all of it together. So 12 plus a -9, well, that's 3. And 6 plus 6, well, that looks like 12. All right. So all we have to do now is multiply by the scalar and get 3/7, 12/7. And that is the solution to the problem. Now that tells us that x is this number, y is that number, but you can also talk about the point of intersection, as a general point as 3/7, comma 12/7.